Jerry, just before you start, can we find seats for a few people?
Oh, sure. Yeah.
There's one spare seat, there's two spare seats here,
A couple here.
a couple over there. I think for some reason they scaled back our order. I had ordered more than enough, and there's a seat there.
I need to lie down. Thank you, Julie. Okay. Panie I panowie, dzień dobry. Those of you who are Polish, those of you who speak Polish, may be relieved to know that's probably all Polish answers. Even if indeed you were able to identify. So I'm going to tell you about the Cyklometr Mariana Rejewskiego, or Marian Rejewski's Cyklometr. And this is a little story of how you get from something like this, which probably those of you who are into enigmas will be familiar with, via a page that looks like this, with the help of an engineering diagram that looks like this, to a final product that looks like that. I would have brought this, but it's kind of hard to carry around on the London underground system, so I'm afraid you're just going to have to watch the video, of course. Is it been moving around that's making all that cracking? I better stand still a little bit.
I'll take the glasses off the tie.
I think it's the glasses. Yeah.
I might walk into walls now.
That makes a difference. Absolutely.
First of all, I'm going to introduce you, so to speak, to Enigma. Enigma is often thought, or often held to be, a purely World War II phenomenon. They mysteriously appeared at the beginning of the war, and then you get all these fine movies like Imitation Game, Enigma, Das Boot, and so on. But in fact, Enigma goes back a lot earlier than that. And what is an Enigma machine? Well, there is no such actual one thing as an Enigma. I'm contractually required to tell you that what I'm about to show you is copyright Messrs. Paul Reuvers and Frode Virewood of the Netherlands and Norway, respectively. There's about 25 different Enigma machines. And the oldest one it was in 1923, so way pre-war. And this was the 1923 Enigma. It has a printer on the top, and it has 4 rotors here, and it's got lots of cranks and things to make it go. This one's a numeric only Enigma, the Enigma Z, where Z is short for the German word Ziffer, which is German for numbers. And it just goes from 1 to 0. So it just encrypts numbers. Now the point about those machines, they're pre-war, they're actually used for business purposes rather than military purposes. It's not until you get to systems like this, where you have machines with a plug wall on the front and 3 rotors, you start getting into the Second World War era. This is a 4-rotor machine. It's called a Tirpitz. It was actually produced by the Germans for use by the Japanese, so the Germans and Japanese could talk to each other in the theatre of the war. So they didn't have to give the Japanese their own Enigma machines. In other words, they designed one for Japanese use only. Because I guess they didn't quite trust the Japanese totally with the standard issue. This is a very rare machine. It's at the Institut Józefa Piłsudskiego in Hammersmith in London. You may notice it's got a keyboard, instead of being arranged like a German typewriter, it just runs from A to L along the top row, and then J to Q on the second row, and then R to Z on the bottom row. It's actually not, it is an Enigma machine, but it's not made by any Enigma company. And it was produced by French engineers, by Polish, to Polish designs, which were created after the Polish story, which I'm telling you about, had reverse engineered the Enigma from the messages they were receiving. So in a sense, it's a bit like a tunneling machine. It's a reverse engineered Enigma. So although it works like an Enigma, it's designed somewhat differently. It is visible at this museum. It's in Hammersmith, first floor of a Polish social centre. I'm going to focus on just a few of the machines which were in use pre-war. And it's a 3-rotor machine with a plug board and a German typewriter laid out keyboard. Now, just in case there isn't anybody familiar with encryption methodologies, I bet you all are, but there might just be one person who isn't. So I'm going to press on with this bit. Caesar cipher. I've got a very important message which must be kept secret. And I encrypt it just by having 2 alphabets, A to Z, and shifted by 5 letters, F to E. So simple encryption, replace every letter in the message, look it up in the top row, replace it by a letter in the bottom row. And you end up with a piece of text like that, which you then, in order to hide the word divisions, block up into sets of 5 and then transmit. And typically, in fact, you'd also add a few filler characters on here to keep the 5-character block. When you want to decrypt it, it's trivial. You can just try, you can brute force your way through it. Try key as 1, not English. Try key of 2, not English. Leaving out 3 and 4, because I'm sure you've got the drift. Key equals 5, a very important message which must be kept secret. You can also do an analysis on by counting all the letters in the encrypted text, and you notice that J by far outnumbers all the others, and then Y comes second. In English letter frequency happens to be E is the most popular, C is the second most popular, and therefore you can guess that J probably represents E, and Y probably represents T, and therefore by subtracting E from J or T from Y, you get the number 5, which is the number which you first started with. You can make it a bit more complex by maybe adding a number to the alphabet, so having a row of alphabet. So when you're doing the first character, you would have this alphabet. When you're doing the second character, you would have this alphabet. When you're doing the third character, you're using this alphabet, and so on down the page. And when you try and count the letters in there, the distribution has gone much flatter. It's not completely flat, but it is flatter and very hard to try and decipher unless you knew the methodology that's being used. It would be much harder to get back from there back to here. Incidentally, I didn't choose this text particularly carefully, and I was rather pleased when I did the sums that E really was the most common letter and T really was this letter. That was luck, honest. So let's have a little bit more of a look at this machine. There's a plug board here, keyboard, a lamp board, and 3 rotors, and very interesting panel at the top, which people think, oh, that's way cool. I wonder what that says. It must say something really, really secret. And in fact, it's cleaning instructions. Although it does have a warning in there as well that you've got to shut the front cover, otherwise the plugs will fall out, and then you get more than 2 lights, or more than, you may get 3 lights lighting up at once, and so on. So it's not very interesting, really. A little demo of how the machine works. Demonstration of how A could be encrypted to the letter H. So, press on the keyboard letter A. And the current starts to flow. Did the rotors move or something?
Yes,
Thank you. There's a mechanical interlock such that when you press any key, at least one rotor will turn. Possibly two rotors will turn, or even possibly three rotors will turn. In a method a bit like the mileometer in the car, there is a little quirk whereby sometimes these rotors will not quite step regularly, but we don't need to worry about that too much for the point of view of this demonstration. So we now have current flowing out of this battery, positive, conventional current rather than electron current, goes through the keyboard A, goes to the plug board, and then from the plug board, A happens to be plugged into M on the keyboard, or on the plug board, and then current goes through the entry drum, or the Eintrittswalzer, into the first rotor, into the second and third rotors, and then into this so-called reflector, or Umkehrwalzer, and then back through the three rotors, back through the entry drum, back through the plug board, and now finally the light comes on. So you've now encrypted A to H. Because the rotors are moved, the next time you press A, you're more likely than not to get something different than H, although it's not guaranteed. A little demonstration on this simulator. I typed in the letter A 4 times, and it's come out as GDPB, the current having flowed through not only the rotors, but also the plug board. The initial setting of the machine in this case was 3 A's, but the first encryption will be done at AAB, because as I pointed out, the rotors move before the actual encryption is done. So after you have done 4 letters, you end up with AAE. Each of the rotors has the capability of having its outside moved relative to its inside. I have here the rotor which I prepared earlier. This is not from an Enigma, by the way. This is from a Russian machine called a Fialka, but the principle's the same. You have an outer ring and an inner wiring maze, which can be fitted in any one of, in this case, 32 positions. In Enigma, obviously, 26. And in fact, in this case, it can also be turned over, but that's a speciality of the Fialka. So you only have, the ring settings can be one of 26 positions. And there, for those of you who couldn't see what I was holding up, is it's an actual exploded rotor. This ring can be put onto this wiring loom or wiring maze in one of 26 ways. Now, the ring setting is actually not as important as you might imagine, because the ring setting is subtracted relative to the rotor position. So any rotor that was in position B with a ring setting of B is equivalent to a rotor in position A with its ring setting set to A. But it does make a difference to where each rotor, the tabs on each rotor which operate the next rotor, where they are positioned. So it changes the turnover point of the 2 rightmost rotors. The leftmost rotor doesn't turn another rotor, so its turnover points don't matter. The rotors are typically enumerated with Roman numbers. And towards the end of the life, the active life in Enigma, they went as far as 8. But at the time we're talking now, we're talking 3 rotors or 5 rotors. And the reflector, the device at the left, typically 2 of them, B or C. Different machines, could have different numbers of reflectors. The key settings were typically handed out for a month. In this case, it's September 2010, a little bit post-war. 30 days at September, so this runs from the 1st of September to the 30th. The Umkehrwalz, the reflector at the left, would be one of B or C. The Walzenlage, the positioning of the rotors, and the numbers that is used is defined, in this case 2, 4, 5, and then 5, 1, 2. I'm told that they work up the page because the plan was that after you've done a day's setup, you then tear off the day's information and heat it or burn it or some such, which is why the dates run upwards. The Ringstellung, the rings I showed you on the rotors, adjustable, adjusted on a daily basis. And the Steckerverbindungen, the plug board on the front. Here's a close-up of the plug board. In this case, we have A connected to M and O connected to Y. The machine is fully reversible. Sorry. The machine is fully reversible. If I would type in GDPB, I get AAAA back if I just reset the machine back to its original settings. If I wouldn't have had the plug board, then instead of having GDPB after typing in AAAA, I would have got BDZG. Plug board affects data which is being typed in, characters which are typed in, and characters which come out. Now, if you're presented with a cryptographic problem, there are two known or two defined methods of attacking the problem, the cryptographic problem. Known plain text or ciphertext. Known plain text is where you have an idea of what the message might be, so you assume that that's what the message is, and then you try and get back from the message that you think you've got to try and work out what the encryption algorithm being used was, or in this case, what the Enigma settings would be. And a ciphertext attack in which you have no idea as to any part of the original message. And those of you who are into Tunny and Colossus, I believe you defined the attack on Tunny, the attack on Colossus uses as a ciphertext attack. You don't actually know what the message is. You're not using any guessed at text. Probably those of you who've been to Bletchley Park will have seen they have a sort of slide rule thing where they slide a message along a plain text message along an encrypted message, and they can then discount some of the options because the presence of the reflector ensures that no character can encrypt to itself. So if you have any character that's the same in both the crypto text and the plain text, then you know that that position is not possible and you have to try another position. If you then proceed down a little further, you can maybe guess that it's a weather forecast, Wettervorhersage, and the cipher message was this, and I'm not going to try and pronounce that. And you then produce a nice little pattern, which to me always looks like a bit of organic chemistry. It's called a bomb menu. And then you run it against a bomb. This machine here, I believe, is not a real bomb rebuild. I think it's actually a prop from a movie. I suspect she's not a real person either. There is a piece of software online that's produced by two gentlemen in Sweden. It's not, I didn't write it. I did help to write the manual, so if the manual is incomprehensible, then you have me to blame. And you can put in the bomb menu and wire it in the back in a nice simulated fashion. And it's quite good fun to play with. There's also a 4-rotor bomb. There's one example left in the world that I'm aware of, and it's in a museum in Maryland in the USA. But I'm not going to say any more about the Turing-Boschman bomb, or indeed the Joe Desch bomb, because that's another subject for another day. And I'm sure there are people here who can give much better lectures on these bomb systems. So, ciphertext attack, the second option. We're now in a strange environment where you have a key for the day, which is 3 letters, and you pick 3 letters for a message key. And you're supposed to pick a different message key for each message. And you're not actually supposed to have any real relationship between these letters and these letters. so it really should not be, for example, B-E-R-L-I-N. Then, using the daily key, you encrypt the message key twice to get 6 characters. And you then encrypt the message using the message key. So you've got 6 characters which have been encrypted using the daily key, and the rest of the message which is encrypted using the message key. You then transmit your message, and then when it's received, let's just forget about that for a second. Then when it's received, you know what the daily key is, so you decrypt the first 6 letters, which gives you the message key, and then you decrypt the rest of the message using the message key. And all being well, you end up back with the quick brown fox jumps over the lazy dog. An interesting condition can arise where, given that you have 2 sets of 3 characters, you could end up with 2 characters in either the 1st and the 4th position, or the 2nd and 5th position, or the 3rd and the 6th position, which are the same. And that's an interesting condition because it means you've got the character here which is the same as the character here. And when you've encrypted it, you have a character here which is the same as the character here. And that's an unusual condition. It's an unlikely condition. I've heard it called samica, which apparently means females, although that's actually a bit of a pun based on the Polish word meaning the same. But I'm also told by a famous Polish author they're also called oculari, eyeglasses. And he says he's found that in some of Rejewski's memoirs as well. So, and you can see why you could call them eyeglasses, because if you've got this string of text and you've got 2 characters shining out of the middle, then it does maybe look a bit like a pair of eyeglasses looking out at you. Because the conditions when those coincidences occur, when 2 characters are the same, you can create some what are called płachta cygalskiego, or cygalski sheets. And I've just got a couple here which I thought I might just pass around. People have a quick look at. You're welcome. And Marian Rejewski, who's really the kind of hero in all of this, a mathematician, says rather vaguely, if you've got enough of them and you superimpose them and move them around in the right sequence with respect to each other, then the number of visible apertures gradually decreases. And if a sufficient quantity of data was available, then there finally remains a single aperture, probably corresponding to the right case. That is to say, the solution. That is to say, you found the start positions of the message that was sent. And I tried this, I tried stacking half a dozen of these together. And it really doesn't actually seem to work that well. A real credit actually to the people who made these things. I just printed these out on projector transparencies. They were actually originally hand-carved in cardboard, as I understand it, with a knife. So I decided that a software solution was probably better, and I was then able to write a piece of software that could eventually have a single aperture in the right place, telling me what the original Enigma settings were. A slightly more automated way of working this out is a device called the bomba Marian Rejewski. I did say I wasn't going to say speaking more Polish, didn't I? I can't help it. This, as you see, has 6 stacks of 3 rotors, and it runs them mechanically. It's the origin of the name bomb, as used in the Turing version of bomb. The reason why it's called a bomba is subject to discussion. I don't know if anybody really knows. And there is a simulator available from this gentleman, Marian Rejewski. And I'm not allowed to give it to you because actually he uses it as part of a competition which he runs every year based in Poznan. Finally, I'm going to mention metoda Cygara Rejewskiego, or the gentleman's clock method, which is a statistical method of comparing two encrypted messages of which one has a known start position. So if you crack the start position of a message, you could then consider using this clock method to see if a second message could have a start position close to the first message. And this was either reinvented or rediscovered or reappeared as Banburismus at Bletchley Park. Right. One quick changeover. Part 2. So we're back to Marian Rejewski. So Krakowałem Enigma. I cracked Enigma. Those of you who are in the front, maybe have seen the background is actually Colossus. So there's a little bit of poetic license or artistic license being used here. Marian Rejewski, 1905 to 1980, Polish mathematician and cryptographer, who in 1932 broke the German Enigma cipher, Enigma, with his colleagues Henryk Zygalski and Jerzy Ruzicki. I'm just going to point out a little place in Poland called Poznan. It's about 3 hours by train from Berlin. In a square outside the university building, I guess, there is this nice little Toblerone on end, which celebrates Marian Rejewski, Jerzy Ruzicki, and Henryk Zygalski. And you'll note there's a lot of numbers up here, and there's been quite a lot of debate as to whether these numbers mean anything, if there's any messages encrypted in there. And conspiracy theories abound, and as far as we know, they're probably just random. But I discovered this quite by mistake when I was in Poznan, as can happen to a chap when he's not expecting. And my wife was so amazed that I found this thing that I was so amazed that she insisted on taking a picture of it. Now, on a handy website called spybooks.pl, there's a lot of documentation, mostly in Polish. And this one is fairly seminal. Wspomnienie z pracy w biurze szyfry. My memories of my work in the Cipher Bureau. And this is the page that excuse me? This is the page that we're going to start with now. Incidentally, I'm going to mention that a lot of these memoirs are written on a French typewriter. Polish has all of these accented letters, and there is no intersection between the French accented letters you get on the typewriter and the Polish accented letters that you need to type Polish. And that means you do see places where accents are being written by hand. Now what we have here is, let us assume that on a given day we have the following messages. And these are the first 6 characters of messages that you have received, which have been encrypted by Enigma. And each of these 6 characters represents the same 3 characters which have been encrypted twice, using 1, 3-character key. And you can see that you have a case here where there's an A in the first position and an A in the second position. But you can see here there's a case where there's a B in the first position, which becomes a C in the second position, and then there's a C in the second position, which becomes a B. So C in the first position, which becomes a B in the second position. So you have a little bit of a loop or a cycle. There's a clue in that word cycle. You have here the case where there's a D, which becomes a V, and then a V which becomes a P, and a P which becomes an F, and so on. And I'm not going to go through the whole cycle because I happen to know it's about 10 characters long. But if you then gather up all these characters and write them out, you can say that for the permutation for the first and the fourth characters, you have D, V, P, F, K, X, G, Z, Y, O, and E, I, J, M, U, N, Q, L, H, T, and you have two letter cycles, B, C, and R, W, and two one-letter cycles, A and S. And you can repeat that for the middle characters, so you have a U which goes to an N, and then an M which goes to a B, and you can produce the second line, which is B goes to L, goes to F, goes to Q. And you now have what, if you like, you might like to consider as a footprint for that particular day's messages, a fingerprint. The actual letters that you find in here are not necessarily significant, because they could have been edited by plugboard, either edited on the keyboard or edited on the map board. But the actual numbers that you're looking at here are then important. And a device which Marian Rejewski designed, the Cyklometr Marian Rejewski. I decided to simulate that, first of all, by using two Enigma simulators. So I have two Enigma simulators. The first one I set to JXG, 3 random letters. It has to be my wife's initials, but you don't get to know what the X is. And a second simulator, JXJ, 4 letters on from JXG. So, on JXG, I type in an A and I get a Z. On JXJ, I type in the Z that I got from the first simulator and get an F. Back to JXG, I type in an F and get a K, and so it goes on until I've used up all the letters that I can, all 26 letters, creating the cycles, just using two Enigma simulators. EWR and EWU gives me some more cycles. JFK and JFN gives me another set of cycles. So I was beginning at this point to think this actually works. I can get unique cycles, I can get cycles that are actually cycles. This is an earlier picture from Marian Rejewski's original, earlier documentation. Up here you have 3 rotors. Item 1, Okura Vuniku Zamknięta, which just actually means cover closed, cover open. Rotor cover open, rotor cover closed. A rheostat. Now, the presence of this rheostat, I have heard people thinking that you're supposed to crank it as a handle, and each time you crank, something happens. But the point is, you've got 26 lights in here, and say they're all 4-volt lights. When they do light up, and I'll show you the circuit diagram in a minute, you will have all 26 lights in series, and if they're 4-volt bulbs, you need 100 volts. If only 2 lights light up, and you apply 100 volts to the 2 lights, which are now in series, of course you're going to need 2 new light bulbs. So the deal is you're supposed to put the rheostat down to 0, and then apply the settings you want to apply, and then gently crank up the rheostat until the lights come on, just enough to see what they are, and then switch it off again, and then do the next settings, and then crank up the rheostat again until you can get the lights on. So it's kind of error-prone, really, because you just have to be a bit too enthusiastic with this rheostat, and you end up having to replace all the bulbs, or half the bulbs. You can consider the operation of the machine as, here we have a case where there's 2 rotors, which are being unfolded, if you like, onto strips. We're considering also the case where the 6 characters that you're interested in, no turnover of either of the left hand or the middle rotor has occurred. So you can collapse the reflector and the 2 left-hand rotors into one fixed rotor. And you can see there's some power supplies indicated here and a couple of lamps showing. And I decided to try this first of all on paper, and I wasn't going to mess with 26 position rotors. I just set up 6 position rotors just to make sure that the design works. And the design does seem to work. I was able to get 3 different cycles out of that. And then I decided the next stage has got to be to actually make one. Once again, only 6 positions. So there's 2 reflectors here at the ends, 2 rotors which can be slid up and down in these slots. A section in the middle for the lights. And the rheostat, I didn't bother with the rheostat, I just used the constant current power supply. And then with the rotors in various positions, there's no actual contact between the rotors and the LEDs and the rotors and the reflectors, so it's all being done by wiring. And I can make rather nice, pretty lights come on, thereby at least proving the point. I then shifted the lights off the board into a separate lamp and switchboard. And I thought, well, why don't I try and produce something a bit closer to this? So I looked at some prices of actually buying 3 rotors, buying one of these and buying one of these. And at the time, it came to about $10,000, which was at the time about £7,000. It was probably closer to £10,000 now, probably. So that didn't seem to be the way ahead. Right, on to phase 3. Phase 4. So it seems to me that I could replace a lot of those mechanicals with a PC and just simulate the 6 rotors and the reflector in software. With a general purpose input-output board with 26 LEDs connected and 26 switches connected and 6 more switches for controlling the rotors, the pretend rotors, and a point-of-sale display. The software that's being used is basically a number of Enigma simulators all built into one piece of software, such that now when you type in an A, you get the cycles all the way through the rotors. So A encrypts to U, which then decrypts to F, which then encrypts to T, which decrypts to H, which encrypts to Z, which encrypts to A. And you can work your way through every single switch position with every single rotor possibility, and I in fact selected to use all 8 available rotors, and you end up with something like 300 megabytes worth of text file, which is more than you want to try and handle using a card index, but fortunately today's PCs are well up to it. A little bit of analysis you can do. You can sort in order of the cycles, and you can do a bit of counting of the order of the cycles. So if you've got a set of messages with fingerprint that looks like this, then there's only one message setting it could possibly have been. On the other hand, if you had a message with a fingerprint that looked like this, then unfortunately there's 1.5 million possibilities. So you want to hope that you get mostly messages with this up in this area. The hardware is Points of sale display. I think in the words that were read out about me earlier, it did say I worked in retail systems, and this is where I took advantage of my work in retail systems. And a box with switches and lights. And I would have bought the machine, but as I said, carrying it on the tube is not something I want to do. So let's just have a And now I'm going to explain what you were actually seeing. So, this is the two-line display, and this is the keyboard and lamp panel. And I've set the two rotors to AAA, the two rotor sets to AAA and AAD, selected one for the leftmost rotor, two for the center rotor, and three for the rightmost rotor. And the software actually tells me, it kind of guides the user in a way that they would not have had in real life. It tells me that the first character I could type in would be an A. So I press A, and it immediately lights up A, F, H, and T, U, and Z. So I now know that the first piece of the fingerprint for rotors 1, 2, and 3, AAA, AAD, is 2 3s. The system's telling me that I can use B next. And when I do a B, it comes up with 18 lights, 2 cycles of 9. And the system then tells me that actually there's not very many letters left to try. You could try a Q, and that tells me, just with the lights Q and V, that I've got 2 1 cycles, 2 3 cycles, and 2 9 cycles, adding up to a total of 26. Then step the rotors on one step in synchrony, AAB and AAE. And now I've got more positions for the AAA and AAD, and I'm starting a new fingerprint for AAB and AAE. And this goes through like this. And eventually you end up with a set of 3 permutations for the first setting, 2 for the second setting, so 1 for the third setting, and you just keep going through this manually. That's how you would have to have done it with the original machine. Fortunately, I can leave my machine running overnight, and the next morning I've got roughly a gigabyte of text file to play with. Let's get on that one. So, we've got from there via there. I did wonder if the combinations shown in Rejewski's documentation were actually feasible. What you have here is the 3 permutations, 1, 2, 10, twice 1, 3, 9, twice 13, 13. I checked through my gigabyte of data and determined that if there were 8 rotors, there are 1,791 positions where that condition could occur. With only 3 rotors, there are only 32 positions. If you want to do some further reading, there's this fine book here. Wspomnienie de mej pracy, Obierze Chiffrów. And if you prefer it in English, by a bit of magic, you can turn it over again in English. And that is how these three gentlemen, Marian Rejewski, and Henry Cyklometr, broke Enigma. Here we have the colours of the Polish flag and the broken Enigma logo. And that's it.
Question is raised. Oh, sorry.
Yes, I looked into the studies, females business some time ago, and I think that every female you get halves the search space, and you need something like 200 to crack the code in a day, on the same day. Which is interesting statistics. Of course, they stopped doing it at the fall of Paris. They stopped putting the double encoding on first.
Well, yes.
The method collapsed.
Yes, all of this is an evolutionary dead end.
Yeah. The other is you just passed around the plastic sheets. I noticed that those plastic sheets appeared in the imitation game very briefly for about a second, without any explanation.
Yes.
And there were the modern plastic ones, not the original cardboard ones. I didn't bother to cut the cardboard ones.
Yes, so just one question. So have you studied the complexity of the attack? How many pairs with females would you actually need on average to cover the key, to know the setting?
Females, which is not the cyclometer. Well, if you're using Cyklometr sheets, it looks like you only need half a dozen or so to get a unique result. But you have to do it for each of the possible first row positions. So you have to multiply that half a dozen stacks that you're going to do with the number of possible first roses.
Okay, and what is the complexity here with Cyklometr? How many headers do you need in order to be able to know the total setting, what kind of an average or typical quantity of messages you need?
You need enough messages that give you all the 26 letters in the first column, so that you can then produce all the cycles that relate to them. And this all assumes that there's no turnover as well.
Okay, so there is no precise estimation of complexity.
No.
Rejewski did not produce some sort of rough figure from experience.
Not that I determined, no. The example given actually has too many examples for the case. And he's actually doubled up on some of the pairs in that screen.
Just one small remark. I think you have said that the Fiałka rotor has 32 contacts, but I think it has 30.
It may be, yes.
Yeah.
Just did a quick trying to remember how many letters there are in the Russian alphabet. I know there's a few letters.
less than letters Russian alphabet.
Yes.
So, yes?
Yes, you handed round these,
I did.
and I was surprised. I expected them to be random,
Yes.
and in fact, I see that half of it is duplicated.
Yes. That's so you can overlay. It's a double sheet, yes. It's so you can overlay them.
No, sideways.
And top to bottom.
Yeah. Okay, and that's to be expected, is
Yes.
it?
Yeah.
Okay. Right on.
I'll ask a question. When was this work done?
Oh, pre-war.
Oh, right,
I don't
okay.
know the exact year.
533.
Excuse me?
They broke in just in time for Hitler to become chancellor. So just in time for...
Peter,
Sorry.
no one can hear you, so.
Just in time for 1933 and Hitler to become
Yeah, there you go.
chancellor. So just in the nick of time. I think the gentleman's question infers as well, if I remember rightly, the cycle pattern is different depending on which rotors and so on.
Oh, yeah.
So it's a question of luck. So
Yes.
for certain orders it's horrendous, and for certain orders it's not so bad.
Yes.
And so it's very difficult to say.
Because as I pointed out, if you had 213 cycles, there was 1.5 million possibilities of that fingerprint. If you had and there was a unique one at the top of the list, which was mostly ones and then a couple of twos, if I remember So there could be days when work would be useless.
About 15 years ago, when I started volunteering at Bletchley Park, the statement was made that the bomber, Turing's bomber, had got no relationship to the bomber of Pulse.
Yeah.
How do you view it with the other 15 years worth of research?
Well,
is there some relationship, do you see?
I think there could be some relationship, and I suspect you could wire a Turing Welshman bomber to work like a Marian Rejewski bomber. And the gentleman in front of you is nodding.
I saw another hand go up actually. Good.
If I might take you away from code breaking strictly for a moment. Something you said struck a chord with me, that the whole thing is dependent on a battery inside the machine, inside the Enigma machine.
Yes, okay.
And it struck me that under field conditions, this is something of a drawback. It's either got to be very heavy or you need to recharge it for climates, which is not the very easiest thing to do under field conditions. Was that a problem?
I think the Enigma might also have an external feed, or at least some of the models, but I'm not sure about that. They certainly used a 4 volt or 4.5 volt, I believe, dry battery, which people now resell refurbished with 3 triple A's and 3 double A's in the original box.
At least the replacement wasn't produced by Samsung, I suppose.
But actually, the actual current usage is very, very low, because when the machine is not being used, there's no current flow anyway. So you're only driving one light bulb at a time when you're actually using the machine. The rest of the time.
Filament bulbs here, which is not easy to take
I was looking for you earlier, John. I was expecting a hand. There we go.
Just one small thing. I thought you said you showed up a wiring diagram. Did I nod off at that moment?
I showed you a wiring diagram of the thing with 6 position rotors drawn out on a piece of paper with coloured links. And then I showed another wiring diagram showing basically a PC on the left and a 2-line display on the top with the lamps and switches and GPIOs below. But I haven't gone into any more detail than that.
I was thought perhaps you were doing the cyclometer or your own version of the cyclometer wiring diagram.
It's very boring because there's 26 switches leading to 26 GPIO I/O ports. And 26 LEDs being driven by 26 more GPIO ports. But if you need more details, I'd be happy to provide them.
Thank you, Joe. I'll pass the microphone.
Sorry, I was standing behind you. Just to say, in fact, I was watching daytime television the other day, sort of thing us old blokes do. And on the PBS channel, there was a very good documentary about the history of Enigma, the Polish contribution, the Welshman Turing contribution, the development of the Geheimschreiber, Colossus and where it fitted, and so on.
Yes.
Absolutely amazing. It was American. It was narrated by Charlton Heston, didn't once mention guns. Well, not in that context. But in fact, it was a very, very good overview of the history of this whole project. And being on PBS, it'll probably be repeated over the next 2 or 3 days several times.
Well, there's a zillion of these things on YouTube as well.
Yes.
Well, ladies and gentlemen, I found that absolutely fascinating. And you could have heard a pin drop through an hour of really quite intense stuff to keep our attention on what is a complex subject so well. I think is outstanding. And I'm sure everyone will join me in thanking you for a really, really good and interesting presentation. Thank you very much.
pleasure to perform on behalf of BCS. They're getting more generous since I was president. That for speakers who give such an outstanding show, would you please accept this small gift? It's a pen at one end and a 4 gig something right there. Processing from the year dot from 1 hour to every day. You have to be careful about the what you hear on American television. Nothing to do with Bletchley, I'd say. But this, I actually heard this, and I couldn't believe it. You know, Bob Dylan got the Nobel Prize for Literature, and they interviewed this chap in America who pointed out he changed his name to Dylan after that famous American poet, Dylan Thomas. I couldn't resist it, so you gave me the I just want to give the parish notices, if I may. Bear with me for a moment. On the 17th of November here is the Sale Award ceremony and a presentation from the winner. Then on the 15th of December, it says interestingly here, computer films. That's a broad title, interesting. And then going on into January, I won't go through the whole list because they say the excellent website showing all the programme right through, but on the 19th of January, History of Enterprise Systems. That might be something I can understand after all this, so look forward to that one. So it just remains for me to thank the speaker again. Thank you for coming, and I very much look forward to meeting some of you afterwards and meeting you at the next session. Thank you very much.